Welcome back everyone to week 6 and 7 of this course. So we'll be looking at geometric dimensioning and tolerancing techniques, shortly called as GD&T. So till last week what we have seen is, we have seen an overview of the manufacturability techniques, and this week we'll be focusing on two topics, that is the dimensioning as well as the tolerancing technique. So moving forward, this is the brief overview of the topics that we are going to cover in the next 2 weeks. The first is what is GD&T and what are the common usage references or the standards for this GD&T, following which you will have the dimensioning technique. So we'll look in the dimensioning part of GD&T. So we'll look into what is features, what are types, what are the different symbols that are used for dimensioning, and what are the rules to be followed when you dimension different features and objects. Next, moving forward, it's an important topic of tolerancing. So we look into what are the different definitions of tolerancing, what are the specifications of it, and we look into several key terms, the size, limits, deviation, followed which we look into datums. So that is an important terminology used in tolerancing. So we look into what are frames, references, and simulation pertaining to datum. And next we'll look into the allowances and clearances, which is then applied to fits, and then we'll look into various international tolerance grades and what are the different features wherein different grades are called for. Next, we'll dwell a lot into various GD&T symbols and their modifiers, and we'll touch a little upon the virtual conditions, and finally conclude with the different GD&T rules that are to be followed. So this is a typical GD&T encoded drawing that you see in a technical drawing. So as you could see here, you have your object here that are referenced by several dimensions. So first we have seen a basic dimension, then there's a leader, then there's a datum feature, then there's a feature control frame. So all these things we look into detail, how it's going to affect the manufacturability of this object, and then the quality standards, the inspections of this object in detail. But this is how a typical GD&T drawing will look like. You can see different boxes are coming in, there are different symbols, there are different notations. So all these together are decoded to ensure that the object is manufactured and inspected to satisfy its feature or function. So now we'll come down to what is GD&T. So first you design whatever object you are doing for three things. That is, you design for manufacturing, assembly, and service. It means that your design should be capable of manufacturing using the commonly available techniques or based on the desired requirement of you. So suppose it requires for a special manufacturing process, then you have to adopt it. You have to know what are the different tools that you have under your disposal to ensure that the design comply to those manufacturing processes. Once that is done, how this design is going to be assembled together. So there you have different components that are going to come together to serve a function. So how are you designing those objects, the individual components, to deliver a overall performance? So that is your assembly. So once you have assembled and then the object or the material has gone to the customer, the intended person, and then it goes on to its useful life, and suppose if there is some requirement of service coming in, then how is your design catering to ease of serviceability? So this is the broad spectrum of design bringing into different categories, design for manufacturing, assembly, and service. So once you have decided on your design, then you move forward to drafting that design and then releasing the drawing. So releasing drawing, you mean by your verifying all the parameters that are required to put into you, ensure the quality of the drawing, and then release to consumption. Consumption as in release to the next internal customer in hand, be it a manufacturing line or be it to the next department which take this drawing to integrate into the final release. So this is an important part where you are finalizing your drafting and then releasing them to the stakeholders. So next what you have is your actual manufacturing process. So that is, you start based on your design, you start manufacture your object, put together and put it to use. So once you have manufactured, then you assemble it together. So once you have assembled, then you analyze the part, you look for various critical features, the dimensions, the checkpoints, you inspect them for quality and then release. So this is what we have seen in the earlier session, that is this GD&T is heavily used for your inspection to ensure quality of your product. So this is a typical workflow of a product design and manufacturing and service. So where now GD&T comes into play. So GD&T is typically an international standardized language that is used to describe the shape, form, fit and function of each feature of a part. So this part is what we have spoken about earlier. So that goes through all this process. So we use these techniques in GD&T, these set of rules that are common language that can be understood by anyone who is familiar with this GD&T techniques, can use that to describe what is the shape of the object going to be, what is the form of the object, and how the fits of the objects that are going to interact within each other, and what is the total function, whether as the individual feature or as the assembly. So next, how to bring together all these things. That is, you have to communicate this details, the shape, form, fit and function. So how are you going to do is by using a system of symbols, then system of rules, definitions, and with these three we used to define the geometry, that is the four features that we have spoken about earlier, and also the tolerances of the mechanical components without any ambiguity. So this is the catchword here. It means that whoever trained person looks into the drawing can understand the functionality without any doubt, so that there is no mistake that can be done into the production or assembly or inspection. So this is where your GD&T is going to play a big part. So originally how it originated is during the World War II, where it saw major application. So how it was took forward was, during World War II there was a rapid requirement of productionizing the the guns, ammunition, planes, warships, all these things in a large scale manner. So there a large amount of people who are involved in it, ranging from drafters, assemblers, machiners, everybody. So everyone has to ensure that the parts that were produced in millions by them are interchangeable and also ensure their functionality, proper functional, because it's going to cost life. It's not about just winning the war, but it's about saving the soldiers and the citizens' life. So this is where the manufacturing domain, the engineering domain during the World War II applicated this GD&T techniques to ensure that all the components that they produce serve their intended functionality, and also they serve as an interchangeable part, that is, they can be easily repaired. So towards this, there are different standards that are being used worldwide. So the predominant one are the ASME standard Y14.5, or you can refer to the ISO standard 2768. So next we'll just briefly look into what are the different standards and the sub features of the standards. So here have been listed all the ISO standards. So suppose the earlier slide we are seeing the 2768. In 2768 we have two different parts, wherein the part 1 denotes the tolerances for linear and angular dimensions without individual tolerance indication. So in part 2 what we have is the general tolerances that are defined for features without individual tolerance indication. So like that we have different variations of this ISO standards for different applications. So this is just an idea for you to look into what standard you want to follow, want to refer, and then what are the different rules or definitions given in it to apply it to your final drawing. So next let's move on to the dimensioning sector. So here we look one by one. So what is dimensioning and how it's defined? So dimensioning is used to describe the size and geometry of a feature, a part or an assembly. So towards this dimensioning you need to have a strong understanding of the engineering judgment and also thorough knowledge of the practices that are required for it, and also the product, the fundamental requirement for it, which needs to be grasped very clearly. It means that the intended product that you are going to design and deliver has to adhere to the proper engineering judgment principles, and also ensure that you have a very strong knowledge of all the processes that are going to be used in order to produce those components. So only then you can give in the dimensions that are both functional and usable. So next, the different classifications of dimensions. So typically it's classified into two types. The first is the size dimension, wherein The dimensions are measures of the size of a feature, and next we have a location based dimension. That means these dimensions details on the locating features or the objects. So next we can also classify the dimensions into three broader groups of dimensions. So it means that inside a dimensional drawing we can categorize them into three different groups based on their application. So the first one is called as a functional dimension. So it means that these dimensions will describe the part functions or the mating relationships. Next we have a non-functional dimensions. It means these functions do not influence the part function, that is they do not affect the function of the intended part or the object. So next we have the auxiliary dimensions. So these dimensions are used only for information purpose and they are enclosed within parentheses so that it is clear that they are auxiliary dimension, that is they give additional info to the drawing, and for this there is no tolerances that is required to be applied to it. So let us classical example and look into how the different dimensions are set into. So this is a day-to-day application. You have your chain and sprocket. So in this chain and sprocket mechanism, the chain links are a key part or a feature. So in this chain, you can see there are different features that are built into it. So to go into the technical drawing of it, a brief of it, this is how the roller chain assembly will look like, and whatever listed here are going to be the functional dimensions. It means that roller diameter, the pitch, pin diameter, these are critical dimensions that need to be controlled in order to ensure that the roller chain delivers its intended performance. The intended performance is transmission of the power from the driver foot to the wheel through the sprocket mechanism. So the roller width is going to control how this internal assembly is going to sit on the external assembly, and the spin diameter is used to control how this roller is going to fit on this pin and how it has a rolling mechanism. It should not be tight, it should not be too loose. So how it's going to be fitted. Next we have pitch. So it means that the relation between one pin to the other pin is controlled by this dimension of pitch. And then this roller diameter with respect to two consecutive rolls will ensure how the teeth is going to get locked between this roller. So these dimensions is going to affect the part function. So that's why you can say that these are all functional dimensions. Then also we have non-functional dimensions that will be required for manufacturing this individual parts. So one such thing is, you can see this plate, the plate that is going to encompass two different rollers. As you can see here, that dimension can be a variable amount because that is not going to affect the part function of power transmission. And then again in this drawing you can see yes, there is a slot that is given that is going to help in the assembly of the parts. Suppose this is your fundamental part and you need to manufacture it in bulk for different applications. In that case, you can also specify an auxiliary dimension for a given application stating that the number of the roller chain components or the sub-assemblies, say it's in 50 numbers for one application, whereas 100 numbers in different application. So in that case, then you can declare them into bracket within parentheses for communicating the auxiliary dimension information. So this is how it's going to vary. So depending on the function, the designer is required to properly dimension the size and geometry of those features and then categorize them according to the various functions and then deliver to the next line. So let's look into what are the different features that are going into the dimensioning sector, that is for a dimension, what are the individual features. So let us look at this example. We have a rectangle or rather square object wherein we have 5 different nomenclatures that are used here. One is we have the dimension line, and then we have a number that is the feature size, then we have an extension line, and then a visible gap here. So this typically denotes a dimension. So with this, anyone can understand that this is going to describe the dimension or the size or the geometry of the object. So what are the features in it? The first thing is the dimension line. So it means that it is horizontal or vertical or aligned or arc based on the requirement. and that along with your extension line denotes where the measuring object is. Suppose if you are going to measure this object, then you have to use these two faces and ensure that between these faces the dimension is going to be of 30 units here. So towards that you have the dimension line as well as the extension line. So towards this extension line, in order to differentiate that as a dimension, we'll look into the various line types of it, but you can see there's a small gap that is drawn into it to indicate that this is a dimension, that is an information or an annotation given to the drawing to describe this function and not a part of this object. So next we have this leader lines. Leader lines is something where you can see an extension like in here. So towards this leader line, we'll look into more into the next week part, but a brief intro here, that is, you shouldn't cross those leader lines. That is, this, suppose if you want to mention the info of arrowhead here, this has to be here and this has to be here. That is, you cannot extend this and then cross this leader line and refer here. So next is that should not be having excessively long leader lines. These leaders should be positioned as close as the object possible to communicate the matter and should not be positioned it externally very far away. And also it should not be parallel to the dimension or the extension line what is mentioned. So there are different angular requirements to it that we'll look into the next slide. So next we have the arrowheads, that it's a part of this dimension line. So these arrowheads should be between these extension lines, and in case there is no space, then they can be drawn outside. That is, they can be drawn in this manner and then the dimension can be fitted inside, but the arrowheads are pointing towards inside the dimension line. So next we'll look into the various types and symbols of communicating the dimension intention. So the types are, as we said earlier, you have a linear line wherein it can convey a horizontal dimension or a vertical dimension or an aligned dimension. Aligned as in an angular that we look into next. So next we can also have an angular one. So this angular is an arcual element, whereas the aligned is a straight line but inclined in a different way. Whereas next also we have different nodes that are available. That is, you can define whether it's a diameter or a radii or a chamfer. That is, you again communicate the dimensional intent to the designer as well as the manufacturer. So this is a typical drawing where you can also look into various symbols. We'll look into one by one. The first application of the dia symbol is here, and next you have a radius, and applicating this diameter and this radius to spherical element, you prefix an S capital letter before these two. So this is demonstrated here. So this is a spherical element here, and hence it goes for a spherical diameter of 50. Whereas this again a spherical element but an arcual one, so you say that it's a spherical radius of 12. And next here for this object is a roller. The external, the bigger one is shown as 40 diameter, whereas here it is shown as 30 diameter. And here we have different arcs. So here the arc radius is 15 for this feature and it is 10 for this fillet. So this is how you define your diameter and radius for arcual element or a spherical element. Next we also have a reference dimension that we said earlier, that is the previous slide, where we see as an auxiliary dimension that is used to communicate information that is enclosed within parentheses. So that is your reference diameter. Next we have a counter bore or a countersink operation. That is when you go for a bolt machining operation, that is in a slot machining operation, then you go for a counter bore or countersink to ensure the fitting of those mating parts and also to positioning and location of those mating parts. So the symbol for counter bore is a open-ended square, whereas in countersink it's an inverted arrow like this. So next feature is the X mark, that is used to denote repetitive times of the specific feature or in locations. That is, suppose if you are mentioning that there are going to be 5 holes of the same dimension that is located along a pitch circle diameter or so that we have done earlier. In those cases you can use 5x to denote that there are going to be 5 holes of those features. So the number of times or the places where it's going to be located can be denoted by the symbol x. Whereas the next symbol, if you are going to denote the depth, how deep an object is going to be, to indicate that, you can use this, a down arrow a button. So these are all available within the CAD modeling software. And next, indication whether this dimension must not be scaled, then you underline the given dimension. Next, to denote that it's the square element, then use a square object here. So that is, you can see in this example, this face is going to be of 42 units in dimension, and that is a square element. So this is your square symbol. Next, if you are indicating a length of an arc, then you type the dimension wherein above it you place a caret symbol. So next, suppose if you are mentioning that a hole is a complete through element, whatever the two surface length may be, the depth of the object may be, the hole is drilled throughout this length. So that is your through symbol. So here, as you could see, we use a combination of symbols and alphabets to denote the various dimensional properties of the object. So this summarizes the basics behind the dimensioning symbols and types and the requirements. So next, let's look into the various rules that are called for dimensions. So different kinds of rules are available in different resources. So we'll just quickly look into the key dimensioning rules that will be required to ensure that your drawing is properly dimensioned and is properly readable. So first thing is that the dimension should not be duplicated in any case, and the same dimension should not be given in two different ways. It means that quickly let us look into an example. So these are two different views of the same object. It's a symmetrical object, and in this case the total width of these two faces have been given as 94 units, and the individual lands has been given as 32 with a reference dimension as given here. But as you could see here, first thing is like this dimension had been duplicated onto this view. That is not proper because it confuses the user as well as the machiner, because the dimensions are controlled features which require supervision or control. So in this case, you have already mentioned here, so there is no requirement for duplicating it. So next is only requirements or dimensions that are required to produce the component or inspect the parts needs to be used. No unnecessary dimensions that are need to be mentioned. So it means that, look back to the previous slides where we said that you're going to use a functional dimension, because the functional dimension is what needed to be ensured to produce the component or use the component. Those only have to be inferred. All other information, extra information, can be typed out as notes or general info so that it can be captured. For example, if you are going to have a rectangular plate with 4 holes that are drilled to it, the key dimensions are the rectangular block dimension as well as the hole measurements and their location measurements. All other details are not required. So only those that are highly required to dimension them has to be denoted. It means that suppose if there is a non-dimension part, the designer intends to say that you can have any dimension as required or as applicable to that object. Quality inspector also would not be concerned to measure those dimensions. So this is why only necessary dimensions need to be used. So next, the dimension should be given between the points or surfaces that have a functional relation to each other. This comes along with the point 2. It means that only those dimensions are needed to be used for functional references have to be used. So next we have the dimensions that always have to be attached to only those views that can describe the feature better. So it means, suppose if you see here, there are two different views of this object, and this info, that is dia 16, has been given to here, and the total length has been given here. All the arc dia elements have been given, and in order to convey that this is going to be a square element, it has been conveyed in this view where it is more clear. So whereas in this view, these dimensions, the internal dimension and the width dimensions, have been interpreted in the wrong way. That means that in order to communicate that this is a square element, the designer had referred to two different faces for dimensions. So this is a poor representation of dimension. So it means that this information is captured in this form, wherein it is represented by a square mark and a cross mark. So this will denote that this is going to be a square element, wherein the these two faces are going to be circular elements. So you must always attach the dimension to the view that best shows the contour of the feature that being dimension, and also these dimensions should always be referred to the parts or the surfaces that have a functional relationship. You can see here this dimension has been mentioned as a chain dimension from here. So this means that this surface is of great importance, so the designer has to control this surface, and only the designer has to be ensuring that these are the dimensions that he has to take care of, the inspector. So only these dimensions have been measured in this drawing. The next rule is that wherever possible, you must avoid dimensioning to hidden lines. That is, do not take hidden lines as referencing. The hidden line is just an intent of the designer to communicate to the manufacturer or the quality inspector that there's an internal structure to it. Inspection properties involve different gauges, and this hidden line referencing cannot be used to gauges properly. So always use dimensions that are referred to given points or surfaces that have a functional relation. So as you can see, everything revolves around the same function, that these dimensions should be functionally applicable and can be functionally measured. So next, also avoid dimensions that go over the object or through the object. That is, they have to always be positioned outside the object to have a better readability. So also, whenever possible, locate the dimensions in the adjacent views possible. So it means that it goes along with this part 4. If there are design intent to be captured, then the dimension data should be given in adjacent views so that they can be inferred together for the designer or the inspector to capture the design intent. Next, for example, if for a circle, it's always measured by its diameter circle with a line through it. And arc means that you use a leader and then mention it as a radius with r element 0.5. So this is typical rule. These rules mostly should be followed, but in certain cases there are difficulties in dimension, then it can be taken as exception. For example, if this diameter cannot be drawn with a circle through it, suppose it has an internal feature, then you can also alternatively use a leader to measure it. So, but these are general details so that everybody has on the same page and can understand the drawing better. So next is, the holes are always located by the center lines and they can be extended and used as an extension line. So it means that the holes that are drilled to it, so they are always referred to the positioning is referred from between those centers. So the gauges will be designed so that the referencings are always between the center line. So you are aligning those production intent along your design intent. So next is, the hole should be located and sized in the view that shows the feature as a circle. It should not be dimensioned to a feature that is going as a hidden line. So only in those view that is clearly visible that is going to be circle and is going to be hole, then only in those has to be featured. So next is, always ensure that you do not cross the dimension line, extension lines or the leader lines. So these are the different rules, and the final rules is that the leaders that we looked earlier can be sloped at 30 degrees or 45 degrees or 60 degrees angles to ensure better readability and better control over the drawing. So these sums up the different dimensioning rules and techniques that the GD&T standard calls for, and next let's look into how to applicate them onto your AutoCAD drawing.